So the power triangle, as I was explaining you, so this is the apparent power, which is the magnitude of our complex power, and complex power is equal to the real portion plus the imaginary portion. This is the real power, and it is equal to S times cosine theta. And this is your Q, which is equal to S times sine theta, where this theta is our power factor angle. Okay. Now, in the title of today's webinar, I mentioned that it's going to be about power factor, real power, and apparent power, right? So let's just quickly review the real power, the reactive power, and the apparent power. So the real power, to put it simply, okay, it's the kW, it's the watts, it's the megawatts, gigawatts, whatever. This is the power that actually does the work, okay? And to keep it even much simpler, you can just think of it in terms of the power that results in the I square R losses. Okay, that's basically your real power. All right. What is the reactive power? Now, the reactive power is not that evident, not that clear right away for most of the people. Reactive power is basically the power that is required to set up the magnetic field in your inductive loads. Okay. In the industry, majority of the loads that we have, your motors, induction, synchronous, your generators typically it's basically not a load, but still, and your transformers and your reactors, they even the cables, they have inductive components. Like the transformers and motors are almost completely, like their impedances are almost completely inductive in nature. Okay. And for cables for large distances, the series inductance of the cables and transmission lines becomes very significant. But what you typically would encounter as an end load is a motor, right? Small, large, medium, however big or small the motors are. And motors have induction motors. For example, this is the equivalent circuit of induction motor, which is very similar to that of a transformer. Motors in their core have very large magnetizing inductance. Now, this magnetizing inductance is a necessary evil. Why? Because without this inductor, you would not have electromagnetic induction. Okay. And in the case of a motor as well as a transformer, the power actually is transferred from one circuit, let's say in the case of a transformer, from primary to secondary, not through an electrical connection, unless you have an auto transformer, not through an electrical connection, but through electromagnetic coupling between the primary and the secondary windings. Okay. And if you don't have this inductor, you won't have that electromagnetic induction. So it's a necessary evil like friction. All of the losses that we encounter, for example, and the energy that is spent when you're running and when the cars are driving and whatnot, when the airplane is flying in the air, all of that energy, the fuel that you're burning, is against friction, right? But friction is a necessary evil because if you don't have friction, you cannot move. You'll always be sliding, right? Because Newton's second law of motion. An object in motion will stay in motion, an object in inertia will stay at inertia, right? So this is a necessary evil. And I don't want to go in too much detail with regards to the equivalent circuit. In P power program, we go through section number 3 of the P power exam preparation. It's all about rotating machines and electromechanical devices. And in FE electrical also, we sort of touch base on the induction machines equivalent network. But in order to fire up this inductor and establish that magnetic field, you need Q. Okay. All right. So the real power, think of it like I square R losses. Q is going to be consumed by the inductor, by this series inductance, by this core inductor, and so on. What about apparent power? Well, apparent power is what it's basically what will get delivered from the source to the load. Now we can change the composition of this Q, right? And P in order to increase or decrease. And the line current, and this is the punchline, okay? The current that flows on the line is a function of this guy. Okay, and I'm going to connect the dots in the next few slides. Is this clear so far? What is your real power? Your I square R losses, basically. Why we need the reactive power to fire up the magnetic circuits, right? In order to establish magnetic field. Okay, electromagnetic induction won't happen otherwise. And what is the deal behind the apparent power? Apparent power essentially dictates how much current is flowing on the lines. Okay, all right. Now, the leading versus lagging power factor. This is a mystery for a lot of people who have a wishy-washy understanding of power factor. Okay. In order to fully appreciate this, we need to quickly review something called passive sign convention. Okay. This is discussed as part of Circuit Analysis 101. And you probably already know it, but I'm just going to present it a little bit formally. Whenever power is consumed, real power or reactive power, okay, it carries a sign of positive plus. This is passive sign convention, which also says that in order for us to have a voltage gain, current must be leaving the positive terminal of a battery, which also says that the terminal through which a current enters a resistor or any impedance or a load for that reason carries a positive um, sign. Okay, so this is passive sign convention. Conversely, if you have a source of reactive power or a source of real power, that will carry negative sign. Now, this has implication. I'm pulling this information from Circuits 101. Circuits is, if I'm not mistaken, section 5 of the P power, 6 of the P power exam. Sorry, FE electrical exam, right? And then you have electronics and power later on. So it flows really nicely. But check this out. If I am presenting a power triangle, right? Okay. And for the imaginary component, which is the y-axis, which is the reactive power, right? Imaginary power, reactive power Q, if it is pointing upwards, and we just discussed that positive Q means that we have a sink, we have a load, we are consuming the reactive power, right? And on the previous slide, I explained to you that your inductors, your motors, your transformers are heavily inductive in nature. Correct? Makes sense? So a load for which its Q is pointing upwards is going to be overall inductive in nature. Does it make sense? Okay. And that results in a lagging power factor. Lagging with respect to what? Who's lagging who? Okay. The lagging and the leading business is always established with respect to the current waveform. Always. No exception. Okay. So when we say lagging power factor, it basically means that our current is lagging behind the voltage waveform. Does it make sense? Right? Okay. Now, what are the implications of this? Just by looking at this power triangle, we are able to now decipher who is lagging who, right? And there is an inherent observation, very subtle observation that needs to be made. And that has to do with the power factor angle. So if you have a Q that is pointing up, the P is always, in the positive X direction because we are looking at it from the standpoint of the load, then you can see that the power factor angle has to be positive, right? It has to be positive. It has to be upwards, right? Now, learning it by contrast is going to help you. Why? Because now let us consider a case where we have a Q which is reactive. Q is reactive, but it is a source. Since it is a source, the Q is pointing downwards, right? So negative Q pointing downwards. And a source of reactive power is capacitor. So we have a load that is connected, which is overly capacitive in nature, okay, with the Q pointing downwards. Just pay attention to the angle theta, how that behaves. it is also negative. There is no other way for this angle to be. Like this angle cannot point upwards if your Q is pointing downwards when you have an overall capacitive load. Does it make sense? Okay. And it has implications because your angle theta now becomes negative. The angle theta over here is positive. And with the help of a practice problem, I'm going to quickly show you why that matters. Okay. So this level of understanding at least is required at the FE electrical exam level. Okay. When we get to the PE power exam, we start looking into the nature of the load as well. In both FE electrical and PE power, they have provided you the um, power triangle, which has the apparent power, the real power, and the reactive power, but they don't include an impedance triangle, which is important to understand because it looks at power factor from the standpoint of the load. So our impedance is made up of a real portion. So if you have a purely resistive load, right, then Z is equal to R because there is a J with a 0x for a resistor. If you have a pure inductive, for example, then you have JXL but a 0R. And same thing for your, so this is at R, this is at L, and this is at C. For ZC, it becomes 1 over J omega C, okay? So that we already know. But how does that apply and carry forward to power factor? Very simply, because just like your apparent power was divided up in the real power and the reactive power component, I can do the same thing with the resistor and the reactance. Okay. Now this reactance can take two forms, right? When this reactance is X of L, which is J omega L, okay, then what happens? We have an inductor, and the L emphasizes inductor. And check this out. Inductor results in lagging power factor. It will cause the voltage waveform to appear before the current, or in other words, the current waveform is lagging behind the voltage waveform. Clear? And we are now just looking at a load and impedance. All right. The nature of the load. And this can be a motor. This can be a purely resistive load like a heater. It can be a transformer from the standpoint of the source, and so on. And when we have a leading power factor, we have XC, okay? XC. And X is equal to XC. If you check out the reference handbook, it is defined as minus 1 divided by omega C, emphasis on the negative sign, right? So this is going to flip the arrow downwards. And as we saw with the previous scenario with the leading power factor, when you had the reactive power of a capacitor, which was acting as a source, the angle is going to turn negative. Does it make sense? Okay, so that's a negative. So the power factor angle is positive when we have a lagging power factor. And the power factor angle is negative when we have a leading power factor. You don't need to memorize it. If initially it causes confusion, just sketch out the power triangle. In fact, the power triangle is given in the reference handbooks, both for FE electrical and P power. Okay, and if you have something in between, this is an example of overly inductive load or overly capacitive load. What do you guys think? This guy here. And feel free to send the messages privately if you're shy or if you want to be, discreet. What do you guys think? You can select host and panelist or everyone, up to you. The way that this impedance is shown, it is overly inductive in nature. Correct? Why? Because this guy is pointing upwards. All right. So if we take a step back in the last 15, 20 minutes, what have we learned? What we've learned is that there is more to the to power factor than just this equation. First of all, that was our starting point, right? So PF is equal to KW divided by KVA is equal to cosine theta. That is a very limited understanding of power factor, right? Then we looked at the oscilloscope explanation as to how you're going to basically see this on an oscilloscope, right? Leading versus lagging, then the power triangle, and then the impedance triangle. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, studyforfe.com.